Hello and welcome back to this channel. Dear students, today's topic is P-channel E-MOSFET and FET parameters. From the exam point of view, we can expect the question like explain the construction and working of P-channel E-MOSFET, and most important part is FET parameters. Definitions of some parameters are expected, you may expect from the exam point of view. So let us start the session. दिस इज द कंस्ट्रक्शनल डिटेल ऑफ पी चैनल ई मॉस्फेट. देखो, इससे पहले मैंने एक वीडियो बनाया है रिलेटेड टू एन चैनल ई मॉस्फेट. प्लीज डू वॉच दैट वीडियो बिकॉज ऑल द थिंग्स आर इंटरलिंक्ड. प्रेजेंटली वी आर टॉकिंग अबाउट पी चैनल ई मॉस्फेट. इससे पहले की वीडियो में हम लोगों ने क्या लर्न किया है, यहाँ पे पी सबस्ट्रेट था और डोप्ड मटेरियल वाज ऑफ एन टाइप. In case of P channel E MOSFET, it is exactly opposite case. मतलब substrate N type का है और dopant material है P type. Remaining all the things are same. I mean, we have already discussed the functions of SiO2 layer in the earlier video, so this remains same. There are three terminals: gate, drain and source. अब इसमें ऑपरेशन कैसे होता है, जैसे N channel E MOSFET में हमने डिस्कस किया. The minority carriers were electrons and majority carriers were holes. In this case, it is N substrate, so majority carriers are negative carriers, that means electrons, and minority carriers are holes. Some of the minority, यहाँ पे गेट पे negative supply अप्लाई करना है इस केस में. So if you apply a negative voltage over here to the gate terminal, some of the minority carriers, that is plus charges, will get attracted towards gate terminal, whereas all the electrons, negative charges, will be repelled away from the gate terminal, because of which a channel is formed and drain current starts flowing. So operation is exactly same, only difference is that in this case N substrate is used and P type of dopant materials are used. So channel, that is an induced channel, is formed between these two P regions. Now, transfer characteristics. If you compare the transfer characteristics of P channel E MOSFET with N channel E MOSFET, you can easily find that it is exactly replica of earlier transfer characteristics. इसमें भी जैसे VT है, you can well note this as VTP because it is for P channel. Typical value is -2 volt as shown in this diagram. If the voltage is less than -2 volt, हम लोगों ने डिस्कस किया गेट को यहाँ पे निगेटिव सप्लाई प्रोवाइड करते हैं. सो इफ वोल्टेज इज लेस देन -2 volt, the drain current is 0. As you go on increasing the negative voltage -3, -4, -5, -6, the drain current starts increasing. This is the transfer characteristics. Then drain characteristics, it is same as that of N channel E MOSFET. अलग अलग values के लिए मैंने ग्राफ ड्रॉ किया. Again, logic and explanation remains same. It is the graph of VDS. VDS is the voltage applied between drain and source versus ID. It is called drain characteristics. मैंने तीन ग्राफ बनाए हैं for अलग अलग, for different values of VGS. VGS is gate to source voltage. So it is for VGS1, VGS2 and VGS3. Again, the logic remains same. Means below certain value of VTP. VTP is threshold voltage for P channel MOSFET. The value of drain current will be 0. After that it starts increasing. This is the ohmic region which we have already discussed in earlier video, and after that the values remains constant. It is called saturation region. Before this point, whatever region is there, that is non-saturation region. This is the symbol of P channel E MOSFET. Look at the arrow. Arrow is outward. N channel के case में this arrow was inward. Remaining things are same. That means basically it is 3 terminal device, and 3 terminals are drain, source and gate. Next important part, parameters of MOSFET. ये part और इसके आगे वाला part, that is non-ideal parameters of MOSFET, are most important as far as exam of EC is concerned. So we'll discuss few parameters. Exam point of view से क्या expected है? You need to write the definition and mathematical formula. See, you don't have to mug up the definitions. मैं आप लोगों को कुछ टेक्निक्स बताऊंगा. यू कैन राइट द डेफिनेशंस ऑन योर ओन. सिर्फ आप लोगों को मैथमेटिकल इक्वेशंस याद रखने. फॉर एग्जांपल, फर्स्ट पैरामीटर इज dynamic drain resistance. Since it is resistance, notation is R and it is R0. It is a dynamic drain resistance. So as the name indicates, it is the resistance related to drain terminal of op-amp. You need to remember few points, like it is basically AC resistance and its value is from 100 kilo ohm to few mega ohms. It is always calculated in saturated region. हम लोगों ने characters discuss करते वक्त ये learn किया है कि two major regions are there, saturation region and non-saturation region. So formula, ये formula आप लोगों को याद रखना है. R0 is delta VDS upon delta IDS. एक vertical line draw किया. How to read it? At. It is read like this. Ratio of delta VDS upon to the delta IDS at VGS is equals to constant. Definition कैसे लिखना है? जैसे ये फॉर्मूला आप लोगों को याद है तो इट्स वेरी सिंपल. डेल्टा इंडिकेट्स चेंज. सो चेंज इन, इट इज द रेशियो ऑफ चेंज इन VDS, that is drain to source voltage, to the change in drain current, because ID is drain current. So simple. Dynamic resistance of MOSFET is the ratio of change in drain to source voltage to the change in drain current for constant VGS, that means for constant gate to source voltage. This is the first parameter, dynamic drain resistance R0. Second parameter, transconductance. Its unit is ampere per volt or milliampere per volt. It is calculated at a particular operating point. Again, if you know the formula, you can write the definition on your own. Transconductance notation is GM. It is the ratio of, देखो formula देखो, delta ID upon delta VGS. ID is drain current, VGS is voltage between gate and source, rather it is gate to source voltage. So ratio of drain current to the change in ratio of change in drain current to the change in gate to source voltage for or at constant VDS, that is at constant drain to source voltage, is called transconductance. Third parameter, conduction parameter. अब देखो, as the name indicates, conduction parameter is responsible for producing conductivity. That means it is responsible for the flow of current. So it increases the current capability. Upward arrow जो मैंने draw किया यहाँ पे, which indicates the current capability of MOSFET increases, rather drain current increases as value of K is the conduction parameter, goes on increasing. दो टाइप्स के MOSFET हमने लर्न किए, N channel MOSFET and P channel MOSFET. If this conduction parameter is for N channel MOSFET, notation is Kn. If it is for P channel MOSFET, notation is Kp. Formula is Kn is W mu n COX upon 2L. W is width of channel, L is length of channel, mu n is mobility of electrons, COX is को हम लोगों ने लर्न किया है कि SiO2 लेयर यूज करते हैं. सो COX is capacitance of oxide layer, rather capacitance of SiO2 layer. Same formula for Kp, only notations are slightly changed. W width of channel, L length of channel, COX capacitance of coaxial layer, and mu P is mobility of holes. Next part is non-ideal IV characteristics, that is current voltage characteristics. So we will be studying some important non-ideal characteristics as far as N and P channel MOSFETs are concerned. First characteristic is finite output resistance. Ideally, this value is infinity. I have drawn the graph of ID, that is drain current, versus VDS. We already discussed this graph. ये graph 0 से start होता है like this. अब if you extend this graph in the backward direction, मतलब हर एक ग्राफ ये ऐसे backward direction में हम लोग extend करेंगे till a point at which all these graphs intersect with x axis पे VDS है. देखो ये पहले ओरिजिनल ग्राफ है, ये अगर हम लोग एक्सटेंड करेंगे बैक साइड में such that it will intersect VDS axis, that means x axis at a one particular point. Let us denote this point by VA, then we'll get this kind of graph. So we are getting a point VA at which we can say charge inversion takes place. Alright, so This point is denoted by VA. It is given by 1 by lambda, where lambda is the channel length modulation parameter. ये हम लोग डिस्कस करने वाले हैं. Presently VA formula is VA is 1 by lambda. Now slope of this graph is 1 by R0, where R0 is finite output resistance. जैसे मैंने बताया, आइडियली इसका वैल्यू इंफिनिटी होना चाहिए, बट प्रैक्टिकली this value becomes finite due to the effect of channel length modulation. This is the formula to calculate finite output resistance. It is VA. VA means voltage of this point. VA upon IDQ. We know that ID is the drain current. Second parameter, channel length modulation. ये मैंने क्रॉस सेक्शन का व्यू ड्रॉ किया है, क्रॉस सेक्शनल व्यू ऑफ अ मॉसफेट. यहाँ पे VGS अप्लाई किया है, ये VDS है. वी ऑलरेडी डिस्कस सच नोटेशंस. ये सोर्स टर्मिनल है, इस साइड में ड्रेन टर्मिनल है. दिस इज द ऑक्साइड लेयर, दैट इज SiO2 लेयर. देन हियर आई हैव ड्रॉन डिप्लीशन रीजन एंड दिस इज द P टाइप सबस्ट्रेट. अब देखो, if VDS is drain to source voltage is equals to VDS saturation, or it is at saturation point, then दिस पॉइंट ए, जैसे हमने डिस्कस किया, पॉइंट ए क्या है, ये ग्राफ हम लोग बैक साइड में एक्सटेंड करेंगे तो दे विल इंटरसेक्ट टू एक्स एक्सिस एट वन पर्टिकुलर पॉइंट. दिस पॉइंट इज वी ए. तो ये जो पॉइंट ए है, इट विल बी एट दिस पोजीशन. नाउ एक्चुअल पॉइंट इन चैनल एट विच आईडी बिकम जीरो, मतलब ये पॉइंट ए, दिस पॉइंट आई एम टॉकिंग अबाउट, जो इफ VDS इज वी सैचुरेशन, तो यहां पे होता है. So actual point A on the at which ID becomes 0, that is inversion charge, moves away from the drain terminal, thus effective channel length decreases. ये कब होता है? ये कंडीशन मैंने बता दिया. इफ VDS इज इक्वल्स टू सैचुरेशन वोल्टेज, पॉइंट ए यहाँ पे होगा. इफ VDS we will increase greater than the saturation voltage, that is greater than VDS saturation, then this point which was originally over here gets shifted over here. That means this point moves away from the drain terminal. तो ये जो फिनोमेना है, because of which the effective channel length decreases, क्योंकि effective channel length पहले यहाँ पे होगा, पॉइंट ए यहाँ पे होगा, तो चैनल लेंथ would have been drawn like this. So due to shifting of this point A, why the point is getting shifted? Because we have increased VDS beyond the saturation value. So this point gets moved away from drain terminal, gets shifted, that means moved away from drain terminal. So actual width of the channel gets reduced. This is called channel length modulation. नेक्स्ट पैरामीटर इज बॉडी इफेक्ट. देखो, इससे पहले हम लोगों ने लर्न किया है, यूजुअली द सबस्ट्रेट टर्मिनल, SS टर्मिनल ऑफ MOSFET is connected to the source and then it is grounded. This thing we have already discussed. But in practical cases, only one MOSFET is not used. Rather, number of MOSFETs are used depending on the application. For example, अगर हम लोग दो MOSFETs यूज कर रहे हैं, जैसे इस डायग्राम में देखा है, MOSFET M1 and MOSFET M2. So they are interconnected with each other. Do remember, दो MOSFET इस डायग्राम में देखा है, and the P substrate, I am talking about N channel MOSFET, तो उसमें P substrate होता है. P substrate is common for both MOSFETs M1 and M2. This is S1, that is source terminal of MOSFET M1. G1 is gate terminal of M1 and D1 is drain terminal of M1. लेकिन यहाँ पे drain terminal of M1 that is MOSFET 1 and source terminal S2 of MOSFET 2 are common. अब ideally this S1 is connected to ground. जैसे this is the equivalent diagram, उसमें भी same देखा है. This D1 and S2 terminals are common. Ideally, जैसे मैंने बताया, S1 is connected to ground. But in practical cases, what happens? If both M1 and M2, both the MOSFETs are conducting, then there will be some voltage. That is, there will be some voltage between drain and source terminal of M1. Because of which, since some voltage is existing between drain and source terminal of M1, S1 is already grounded, but D1 and S2 are common. So since some voltage exists between drain and source of M1 and both M1 and M2 are in conduction, then value of D1 will not be 0. That means S2 will not be 0, but S1 is 0. So there is a difference between voltages of substrate terminal or source terminal S1 and S2 of the two MOSFET. This effect is basically referred as body effect. What happens if there is a difference? Due to this difference, there will be change in the value of Vt. So change in the source body or substrate junction voltage changes the value of Vt. This effect is called body effect. The next parameter is sub threshold conduction. मैंने ग्राफ ड्रॉ किया है, ग्राफ ऑफ ड्रेन करंट रादर रूट आईडी वर्सेस वीजीएस. उससे पहले कुछ छोटा मैथमेटिकल एनालिसिस कर लेते हैं. दिस इज द फॉर्मूला ऑफ ड्रेन करंट. के इज, वी नो दैट के इज द कांस्टेंट पैरामीटर. वीजीएस माइनस वीटी ब्रैकेट स्क्वायर. जस्ट टू रिमूव दिस ब्रैकेट स्क्वायर साइन, टेक स्क्वायर रूट ऑन बोथ साइड्स. तो अगर हम लोग स्क्वायर रूट ले लेंगे एट एलएचएस, आई विल बी गेटिंग रूट आईडी which is equals to root k, and this square value gets vanished because we are taking square root. So vgs minus vt, therefore root id is equals to root k into vgs minus root k into vt. This equation is basically a linear equation. That means it gives the formula of a straight line. So if I will plot the graph of root id, this is the equation of square root id. Id is the drain current versus vgs. Gs is the gate to source voltage. Then ideally graph should be like this. It should be a straight line according to this equation. But in practical cases, the graph is like this, which is shown by this dotted line. Ideally, the value starts increasing, value of drain current starts increasing once VGS crosses or becomes more than VT. Below VT, मतलब 0 to VT, ID must be 0. This is the ideal condition. Drain current 0 होना चाहिए if VGS is less than VT. But practically we are getting this type of response. That means in practical cases, you are getting non-zero value even if VGS is less than VT, जो ideally 0 होना चाहिए. So this particular current or this particular conduction is called sub-threshold conduction. The next part, fifth parameter rather, breakdown effects. अलग अलग टाइप्स के ब्रेकडाउन्स मैंने एक्सप्लेन किए हैं. सो फर्स्ट ब्रेकडाउन इज एवलांच ब्रेकडाउन. अब देखो, वी आर टॉकिंग अबाउट एन चैनल MOSFET. In that case, P type of substrate is used and drain and source are connected to N plus dopant material. So between N plus and P substrate, PN junction is created. अगर हम लोग VDD increase करेंगे, मतलब drain voltage increase करेंगे, it may happen that the breakdown of this PN junction will take place, which is referred as avalanche breakdown. So for drain which is N plus and substrate which is P, a PN junction, if for a PN junction a large voltage is applied, then by increasing VDD breakdown takes place, which is avalanche breakdown. Second is punch through breakdown. बहुत सिंपल है ये. As VD मतलब drain voltage increases, then depletion region exceeds towards source terminal. Depletion region का length बढ़ जाता है. It will exceed towards the source terminal. It causes the breakdown. Actually, it increases drain current rapidly, even if for the small change in the drain voltage. So this is the punch through breakdown. Second, near avalanche. Third, near avalanche or snapback breakdown. अब देखो, source, substrate or drain. We know that source and drain are N type of are connected to the N type of dopant material. Substrate is P type of material, so it forms parasitic NPN transistor. Again, this transistor causes the breakdown. And one more reason is that in case of SiO2 layer, we have discussed the use of SiO2 layer and all that. If electric field across the SiO2 layer is increased due to any reason, then breakdown takes place, which is near avalanche or snapback breakdown. And last is static charge breakdown. We know that in case of MOSFET, the impedance is very high, but at the gate terminal, small static charges are present. These static charges may cause the breakdown, which is static charge breakdown. Now the last non-ideal parameter is temperature effects. There are different parameters which are getting changed with respect to temperature. So first is change in Vt with temperature. We already discussed Vt is the threshold voltage. Actually, this change is given by the ratio delta Vt, मतलब change in Vt per change in temperature. Delta T change in temperature is approximately -2 millivolt per डिग्री सेंटीग्रेड. मतलब 1 डिग्री सेंटीग्रेड से चेंज होगा तो Vt will be decreased, lowered down by -2 millivolt. Second, change in resistance. Resistance of the MOSFET is also getting varied, getting changed with temperature. It is typically 0.7% for each degree centigrade. This symbol is for degree centigrade for each rise in degree centigrade. And third is change in value of K. K is the parameter, constant parameter, but it is changing with temperature. Basically, K is proportional, directly proportional. Yes, and this is for directly proportionality. K is directly proportional to carrier mobility, rather inversion carrier mobility mu, and this parameter mu decreases as temperature increases. So these are the few effects of on the parameters of MOSFET as far as temperature effect is concerned. So that's it for today's session. So dear students, thanks a lot for watching this video.